All right, folks, I'm ready to get started. Welcome back to the end of the 7th week together. So we have one more week, and then you're going to get a little bit of a, let's put this in quotes, break. It shouldn't be a break. You should be working. Enjoy a couple of days and a couple of nights during that time. But again, like I mentioned last time, it's an opportunity. Use it. Get better at the stuff you're doing in this class, at the stuff you're doing in your other classes. Pave a really smooth road for yourself moving forward to the end of the semester so that you kill the second half of the semester and you can walk away feeling really good about what you've accomplished here and just really enjoy your time during the break, the actual break, summer break, without carrying the weight of regret. Because that can erode the ability to just have a really good time, which you all deserve to do because, hey, you've decided to be in school, A, which is commendable in and of itself. B, you're in upper division courses. It's a lot more challenging than normal school is, so my hat is off to you. And you do deserve, a nice respite, a nice bit of break and enjoyment beyond all of this, but not right in the middle of it. Fortunately, for schools that have like not semesters, quarters. So we had quarters at UCSC. That was the first time I'd ever dealt with quarters. And quarters are crazy. Like they just move so fast. It's like they push, they like kind of smush 3 semesters into 1 year. It's crazy. Like the speed is ridiculous. But the one good thing is that spring break happens between quarters. So it's not like right in the middle, like just kind of killing the momentum as it kind of potentially can do here if you allow it to. Hopefully you will not. And you should really, really try to make that the reality for yourselves. Like don't let the momentum that you built up during the semester stop during that break. Anyway, are there any questions about anything before I move forward with today's class? Yeah.
For the paper, I know that you have to do analysis, but does it all have to be in the same topic for each analysis? Like, for example, my brother is doing in class it was about the automotive industry. He kept that like idea throughout the whole paper.
Was it a 308 class or this one? Well, I mean, then he just chose to do that. No, the backbone of the paper is like the economic naturalist approach. So that's the thing that links the paper together, like the fact that you are an economic naturalist and you're using the theory as a filter to explain aspects of life that are not readily observable without that theory. So that's the only common link you need. Beyond that, the observations can be anything. Yeah. So just some verbiage in there, to link them all, emphasizing the approach you're taking. Economic naturalist is enough to kind of create a strong structure that's connective for the entire paper. Other questions? Alrighty, then let us move on with chapter 9. So you finished chapter 8 last time. Opened up the homework for that, opened up a mini paper for it. We'll start chapter 9 today, finish it next week. Chapter 9 deals with costs. So again, we are developing a framework for being able to then understand like the decisions that firms make in various industry contexts, varying in the degree of competition that they might have, which changes the nature of those decisions that firms make, which then changes the market outcomes, the pricing, the output, the profits. So in order to understand all of that, you need to understand the costs that firms face in order to compare that against the benefits, which is the revenues they gain from selling. In order to understand costs, you need to understand where those costs come from. That's why we had to start with the production chapter, which kind of laid out the basic properties of what's assumed to be the most general production process. To give you just a basic intuition about how a production process in general will go and how that will sort of have certain patterns depending on whether the firm is in the short run versus the long run. And so now in this chapter, we take those ideas, we kind of mirror them to get us to the costs that the firms consider when making their decisions. And the costs are varied. And so we need to kind of build up some of the ideas once again. And there will be a short run and long run section to this chapter as well. We'll start on the short run today, start on long run as well, finish long run on Tuesday. And the long run stuff, again, has to do with the situation in which all inputs into production are variable. And thus, the firm wants to target a certain amount of output using the cost minimizing mix of their inputs, the amount of capital and labor that's going to minimize the cost of producing a certain amount of output. We in the long run, we use the model that's similar to the rational consumer choice model with iso-quant curves that we talked about last time being interacted with what are called iso-cost curves that serve the same purpose as like budget constraints served on in the consumer rational consumer choice model. And so we'll interact those two either today or early next week to figure out what that condition is that reflects the firms choosing their cost minimizing output in the same way that we had a condition that reflected the utility maximizing consumption bundle for consumers. The optimal consumption bundle that was most affordable and gave the consumer the most amount of happiness. So that condition has an analog and an analogous version with the production framework, and that's where we're heading. But we have to consider cost in the short run first before we consider cost in the long run. So we'll talk about cost in the short run, then we'll talk about cost in the long run. All right, so cost in the short run. To see how costs vary with output in the short run, we'll examine just a running example where we suppose Kelly's Cleaners washes bags of laundries using some labor and some capital. Again, those are the two inputs into production that we assume are being used by the firm, and we just denote them by L and K. Labor is purchased in open markets at some going wage rate, the market wage rate. In this case, we assume it to be $10 per person. So that is the per unit cost of labor. It is the wage. We assume capital is fixed in the short run. So here's just a very simple tabular representation of Kelly's short run production function. Going from 0 to 1 person, output increases from 0 to 4 units. That means that the marginal product of labor is, in this case, 4 units for that first unit of output. That first unit of an input, which is labor. Second unit of labor hired increases marginal product by how much? 10 units, right? Going from 4 units to 14 total units of output. That means that second labor produced additional 10 units. So the marginal product of labor of the second employee is 10 units. Third unit, we see marginal product is 13. So we see we have what are called increasing returns here in this example initially, as is generally the case. The additional amount of output produced by employing additional units of the input labor is increasing initially. But we see that pattern changes. So going, let's say, from the 5th to the 6th, the marginal product of labor goes can be derived from looking at total output at 5 units, which is 58, to total output at 6 units, which is 72. So that's 14 units. So that is going to be less than 15, which is the marginal product of labor going from the 4th. Wait, did I just? Well, anyway, 4th to 5th, the marginal product of labor is equal to 15. 5th to 6th, the marginal product of labor in this case is equal to 14, so it's diminishing. So it has increasing returns initially, then diminishing returns as a result of hitting that short run wall that we talked about. The total cost of producing the various levels of output is the cost of all the factors of production used to produce any particular level of output. So therefore, it's going to be the cost of capital and the cost of labor. Labor is going to have, of course, the wage as the price. Capital has also a price. We call it the rental rate, R. It's the price of each unit of capital. So a firm is either buying their own capital, in which case they have an implicit cost to having that capital, meaning they could be renting it out and earning some money. So by not doing that, they are incurring a cost to that capital versus them not buying the capital and actually renting it and therefore paying the rental rate directly. So either it's an explicit cost or an implicit cost. Regardless, it is the price of capital, the rental rate. The rental value of each of Kelly's 120 units of capital, let's say they're washing machines, is equal to 0.25, so 25 cents per machine hour. So the total rental cost is therefore equal to 120 times 0.25. So that's 120 units of capital times the 0.25 per unit of capital rental rate, which is equal to $30, which is the fixed cost. The cost that does not vary with the level of output in the short run, the cost of all fixed factors of production. So capital is fixed, it has a cost. That cost doesn't change in the short run. Generally, if the level of capital is fixed at some general fixed value, K naught, and R is the rental rate per unit of capital, then the fixed cost is equal to the product of that, the amount of capital times the cost of each unit of capital. So that's our fixed cost, R times the fixed unit of capital. Other examples of fixed costs include property taxes, insurance payments, interest on loans, and other payments to which the firm is committed in the short run and do not vary with the level of output as it varies. And that is also what business managers call as like overhead costs. So that's what we're talking about. We're talking about fixed costs, like the overhead costs, the costs that are not changing as you're changing the scale of your operation, as the firms are increasing how much they're producing. As they're increasing more of their producing, as they're increasing more of what they're producing, they are hiring more people. That's the only way to increase how much output they're producing. And so they have, of course, a variable input they use for that, assumed to be labor. That labor has a price. And so as more output is produced, the only cost that is changing is the variable cost. More and more people are hired, more and more people have to be paid. So the variable cost is the cost that varies with the level of output in the short run, the cost of all variable factors of production. If L1 is a quantity of labor required to produce an output level of Q1, and W is the hourly wage rate, then the variable cost of some amount of output, Q1, is equal to, obviously, the product of the amount of labor necessary to produce Q1 units of output times the price of labor, which is, of course, the wage rate. So that's the variable cost. So, of course, when you sum the fixed and the variable cost, you're going to get the total cost of producing a certain level of output, the sum of variable and fixed costs. So total cost of producing Q1 units of output is equal to the fixed cost plus the variable cost, which is equal to the product of the rental rate times the amount of capital plus the product of the wage rate times the amount of labor. So again, here we have a sample production function that's reflecting certain costs associated with it. We have a fixed level of capital that carries a fixed cost of $30. Going from zero to that first labor yields a marginal product of 4 units. Gesundheit, hiring that first labor costs $10. So total cost is equal to the total cost of producing those 4 units is equal to the variable cost, the cost of wages, plus the fixed cost of capital, which is equal to 40. 30 plus 10 equal 40. Obviously, that relationship holds as we move down the table, representing increased amount of output. Fixed cost doesn't change. Variable cost does as we hire additional folks to produce more. And so therefore total cost is increasing because variable cost is increasing, and at every level of output, the sum of fixed cost plus variable cost will equal total cost. All right, so once again, going back to the production function, the total product curve in the short run, limited by a certain amount of capital that's fixed, reflecting the relationship between output and the amount of the input labor. There's that story that I've told a few times that reflects the fact that initially the firm's hiring some folks and they're dividing up the tasks, and so there's specialization that they benefit from, which results in increasing returns to labor. Marginal product is increasing up until, in this case, I think it's 4 units, at which point the firm hits that short run wall and the employees start to get in each other's way, not have enough capital to go around, which means that hiring additional folks will yield positive amounts of output, but less than the prior persons hired. And so the marginal product of capital will start to diminish or decrease over this range here. So we have diminishing or decreasing returns to our input labor over this range. We have increasing returns to our input over this range here. So here's our total cost function, and we see that it's kind of like a reflection of the production function. It has a similar shape, but kind of turned upside down. So here's our total cost curve. So the total cost, again, is equal to the sum of the fixed cost plus the variable cost. Fixed cost is not changing, so this curve represents the fixed cost. In this example, it's $30. Variable cost is the difference between total cost is total cost minus fixed cost. So graphically, the variable cost curve is essentially just the total cost curve shifted down by the amount of fixed cost. So at any given level of output, you look at the variable cost, you look at the total cost, the distance between the two will equal fixed cost, which should equal 30 because it's not changing. So the distance between these curves will always be the same. Now, the reason the curves are shaped in the way they are is because of what we've assumed of the production process. Initially, there are increasing returns. Each additional laborer provides more output than the prior one. That means each additional unit of output costs less than the prior unit to produce. And so that means that the marginal cost, the extra cost of producing additional units over the increasing returns to labor range will be decreasing. And the marginal cost is, as you would probably imagine, the slope of the total cost curve, the change in total cost with respect to the change in 1 unit of output. And so over this range, we can see that the slope starts to kind of flatten out over this range up until a certain amount of output. That means that the marginal cost is decreasing, and that is, again, due to the fact that there are increasing returns to that variable input. But once the firm hits that short-run wall and the decreasing or diminishing returns start to kick in, that starts to increase our marginal cost. So the slope of our total cost function starts to get bigger, steeper, and steeper, and steeper. Since variable cost is essentially total cost, the total cost curve just kind of shifted down by the amount of fixed costs, and it's going to have that same shape, and the pattern is attributable to the same properties that we mentioned for the total cost curve. So that's why total cost behaves the way it does, because of what we've assumed about production, which is the most general way we can assume production to behave. Other short-run costs. So important costs that are going to be very relevant to figuring out what firms are doing in different market contexts are going to be average costs. So if you have a fixed cost and you divide by the amount of output being produced, you're going to get your average fixed cost. So fixed cost divided by the quantity of output. The fixed cost of producing some output level Q1 is equal to fixed cost divided by Q1. And the thing to note about average fixed cost is that it's always going to be decreasing as long as the firm is in the short run situation, because they've spent a certain amount of money on their capital. That's their fixed cost. You're dividing that by a bigger and bigger number, reflecting a larger scale operation, more and more output being produced. And therefore, this number is going to get smaller and smaller as the firm produces more and more. So there's a spreading effect that occurs with the fixed cost as scale of production increases. Obviously, fixed cost is equal to the product of the rental rate times the fixed amount of capital. So this is equivalent to this. If you have an average fixed cost, you're likely to have an average variable cost. So it's your variable cost divided by the amount of output. The average variable cost of producing a level of output, Q1, is, of course, equal to the variable cost, which is equal to the product of the wage times the amount of labor necessary to produce Q1 units of output, divided by that amount of output, which is Q1. And then, of course, you're going to have average total cost, which is going to be the sum of your average fixed cost and your average variable cost. So it's your total cost divided by the quantity of output, which is equal to your average fixed cost plus your average variable cost. This is super important. It tells you, on average, how much it costs a firm to produce each unit of output. And it's going to have it has a lot of implications for the nature of an industry's competitiveness, which we'll talk about. So again, total cost is going to equal then average fixed cost, which equals the sum, the product of the rental rate times the amount of capital divided by the quantity of output, plus the average variable cost, which is equal to the wage rate times the amount of labor divided by the amount of output. And of course, there is marginal cost. The change in total cost that results from a 1 unit change in output, the additional cost of producing additional units. If we denote the change in output to be change in Q, again using the triangle to represent change, denoting the change in output from an initial level of Q1, and a change in total cost Q1, which denotes the corresponding change in total cost from that change in output of change Q, then the marginal cost at Q1 is given by this amount here. So at Q1, again, producing an additional unit will cost this much. Since fixed cost does not vary with the level of output, the change in total cost when we produce some change in output, additional units, is the same as the change in variable cost. So the only thing that's changing in the total cost is the variable cost, and therefore the marginal cost is also just the change in the variable cost because the fixed cost isn't changing. So marginal cost is equal to the change in total cost divided by the change in output, which we assume to be 1 unit, which is also equal to the change in variable cost because that's the only thing changing in total cost divided by the change in output. All right, so here we can see the relationship between our production, our measures of productivity, and our various costs that we've just talked about. So here's our total cost curve. Remember, the rays represent the average product at any given point where the rays hit the curve. Our total product curve. I'm sorry, this is not the production function. This is the total cost function. The rays here, like they did with the total product curve, represent the average cost of producing at any given point that they hit the total cost function. So at this point, it's just tangent to the total cost function. So at this point, marginal cost is equal to average cost of producing. So the average total cost is equal to marginal cost at this point. And that's going to happen at the point where average total cost is at its minimum. So initially, because of increasing returns, marginal cost will be decreasing. So here's our marginal cost curve. That's this red curve here. Up until this point here, it is decreasing because of increasing returns to labor. And then once the firm hits that short run wall and they start to exhibit diminishing returns to labor, that is when marginal cost starts to be pulled up. Here's our average fixed cost curve, this black one there. As I said, average fixed costs are always going to be decreasing in the short run because there's only a certain amount of money that's been spent on the fixed input, capital, and you're dividing that by a larger and larger number. As we're moving from left to right here, the scale of operation is increasing. So average fixed costs will be spread out more and more and more as we are moving from left to right, as the firm is increasing its scale of operation. Here we have our average variable cost. It's decreasing and then it starts to increase once the marginal cost crosses it. Where it crosses is the point at which the variable cost, the average variable cost, is going to be equal to the marginal cost. Remember, marginal cost is the slope of the total cost function and also the slope of the variable cost function. So if you draw a ray from the origin, just a line from the origin that is just tangent to the variable cost curve, this is the one place where the slope of this line, which represents average variable cost, is going to be equal to the marginal cost. And so that's the point at which they cross. Any point before that, if you draw any other ray before that, we see that the average variable cost is greater than marginal cost, which means that the slope of those rays will be bigger than the slope of the variable cost curve. So the average variable cost will be greater than marginal cost. So that's what's going on over this range here. Average variable cost is greater than marginal cost, but it is being pulled down by marginal cost. So each additional unit that's being produced has an additional cost of production. And as you add that to the total cost that's being incurred to pay for wages, you divide that by labor, that's going to bring down the average variable cost, the component of the average cost of producing each unit that's attributable to the labor, the variable input. So average variable cost initially is decreasing due to the increasing returns. Once we hit that diminishing returns range in production, that starts to bring up marginal cost. Average variable cost will continue to decrease because, again, it is a running average of the average amount of wages that are being spent on each unit of output. And since each additional unit of output is still costing less to produce than the average variable cost, that's bringing down the average variable cost, even past the point of diminishing returns. But eventually, once they cross, that starts to pull up the average variable cost. So once these curves cross and marginal cost equals average variable cost, that starts to bring up the average variable cost of producing, the average amount of average cost of each unit of output that's attributable to the labor that's used to produce it. Average total cost has a similar shape, has a U shape. Over here it starts to go up, and it's not very clear that it's starting to go up. It's not very dramatic, but they do start to go up past the point where marginal cost crosses them. So average total cost is over this range here, again, made up of both average variable cost and average fixed cost. Both of those are decreasing, and so both of those are bringing down average total cost. Once the firm hits that diminishing returns range and it eventually starts to pull up average variable cost, it will start to have a countervailing effect on average total cost, trying to pull up the average total cost, but the spreading effect from the average fixed cost that's also acting on average total cost will continue to bring average total cost down even after average variable cost starts to increase over a certain range. And then at this point where marginal cost crosses average total cost, that's the point at which the diminishing returns effect that starts to pull up average variable cost becomes the dominant component of average total cost, overshadowing the spreading effect of the average fixed cost, and starts to pull up average total cost. So eventually the firm will exhibit increasing average total cost of production, and at the point at which that changes, where it goes from decreasing average total cost to increasing average total cost, is the point where marginal cost crosses average total cost, and it is the point where the diminishing returns effect starts to dominate the average cost of production, and the spreading effect of the average fixed cost of production that's always serving to drive average cost of production down is no longer the dominant force acting on overall average cost of production. Yeah. No, we're not there yet. No. You can't figure out optimal output until you figure out what your costs are, and that's what this is about. We compare that with the benefits of selling, right? The revenues. So that's what we have to do to figure out optimal output. All this is about setting up the framework that the firms consider in relation to the benefits of selling in various market settings, and then we interact those two things to get to optimal outputs in different competitive settings. So that's what subsequent chapters, multiple chapters, will be all about. It'll be all about that. But again, in order to get to that point, we have to really understand this stuff. So you have to really understand like total cost, variable cost, fixed cost. What are those relationships with respect to marginal cost? How does everything relate to marginal cost that's relevant, which is average total cost and average variable cost and average fixed cost? And what are the relations between all these things? And why do they behave the way they do? Well, they behave the way they do based on what we've assumed about production. Yeah. So R1 is just a ray from the origin that helps us to calculate like average variable costs at any point that ray would hit the curve. it is just touching the total cost curve at this point. So that represents the point at which the average variable cost is equal to marginal cost, because marginal cost is the slope of the total cost curve, and the slope of this rate at this point is the average variable cost of producing this amount. And so this point corresponds to this point here, where the marginal cost is equal to the average total cost. We see that this ray crosses the average variable cost curve at this point here. The ray is steeper than the slope of the variable cost curve, so therefore the average variable cost is greater than the marginal cost, which we can verify down here. Here's average variable cost. It's greater than the marginal cost. This ray here is just tangent to the variable cost curve at that point. That means at that point, the average variable cost is equal to marginal cost, which is the point at which marginal cost crosses it, which is the point at which diminishing return starts to pull up average variable cost and starts to have that countervailing effect on average total cost, which eventually overpowers the spreading effect from the average fixed cost at the point where marginal cost crosses average total cost, which starts to bring up average total cost. There's a lot of story behind these curves. They're not just a bunch of curves. I do recommend you kind of sit and just stare at them for maybe a couple hours and just figure it all out. Just make sure you got the whole story down. Really understand the relationships between them, because this is really important just intuitively for just how businesses operate in general, because again, this gives you the intuition about the most general production process. But even when you're out in the world and whatever business or situation you're in is not exactly as the model would predict, this is like the benchmark. This is what you compare your situations in reality against in order to then have some intuition about how your situation is varying from the standard case, and therefore allow you to identify the things that are different, and then be able to develop some strategy moving forward that helps you optimize that situation versus the one that's theorized in the most general theoretical case that we're looking at here. All right, let's do a little bit of math. Practice problem, theory of cost film production. You're the head of a studio and you're trying to figure out how many films to produce this year in order to minimize costs. You're operating under the following production function. So there's the production function. It's a Cobb-Douglas production function. We have capital and labor being multiplied, each being raised to some exponent that's between 0 and 1, and there's some constant coefficient multiplying the entire relationship between capital and labor. Your capital equipment K is solely comprised of film cameras, of which you currently hold 35 units. So K is equal to 35, so that's the short run limitation you face. Each camera is valued at $35,000, so that's the rental rate of your capital, $35,000. You've reached the limit of your capital budget for this year, so you are in the short run. Furthermore, your average labor unit, L, averaged over actors, crew, administrative personnel, etc., costs $125,000 a year. So that's the wage, $125,000. What is your average fixed cost, your average variable cost, your average total cost? What is your marginal cost? How many films should you produce in a year to minimize your average total cost? Go. All right, let's go. One at a time. What are your average fixed costs? So again, fixed cost divided by the quantity of output. So here, obviously we don't know the quantity of output, and therefore we need to derive just an expression for it. So your capital equipment is solely comprised of film cameras, of which you currently hold 35. Each camera is valued at $35,000. So we know that our fixed costs are equal to the amount of capital times the rental rate. So that's $35,000, the rental rate times the amount of capital, which is 35. So the fixed cost is $1,225,000. We're looking for average fixed cost, so that's going to be 1,225,000 divided by Q. So that is our average fixed cost. What is our average variable cost? So we've got variable cost that we know is equal to the wage rate times the amount of labor used. Your average labor unit, L, costs $125,000 a year, so that's the wage rate. And there's a slight trick that needs to be done in order to be able to derive variable costs. Variable costs are a function of quantity. But when we're deriving variable costs this way, we multiply our wage times our labor. But variable costs aren't a function of how much labor we're using. It's a function of how much output we're producing. So we need to construct a relationship between labor and output so that we can then solve for labor in terms of output, gesundheit, in order to get our variable cost as a function of quantity. And so in order to do that, you need the production function. The production function relates labor to quantity. So here's the production function. We know that capital is fixed at 35 units, gesundheit. So we'll get our production function into the short run production function. And now we need to solve for labor in terms of quantity, because that's the only way we can set up the accurate variable cost expression that we need. Because again, variable cost is a function of quantity, not the labor input being produced, being employed. So we just need to solve for L in terms of Q here. Divide both sides by obviously 8.145, and then we're going to raise both sides, in this case to 1 over 0.8, which is equal to 1.25. So raising both sides to the power of 1 over 1.25 is going to get us to this expression here. So this is labor solved in terms of quantity, and we got that from the production function, and that's the only way we can set up an expression for the average variable cost, for the variable cost, which then allows us to get the expression for the average variable cost. So, kind of some like jumping through some hoops here, but it's part of the nature of the model and really what it is that we're studying. It requires it. So you got to remember to take that extra step. All right, so we know that L equals 0.073 Q raised to the 1.25 power. So therefore, our variable cost is equal to the product of our wage times the amount of labor in terms of quantity. So 0.073 times 125,000 gets us to 91.25 times Q raised to the power of 1.25. That is our variable cost. And then our average variable cost, which is what we're looking for, is our variable cost divided by our quantity. So here we've got 91.25. Q raised to the power of 1.25 over Q is going to equal to 9125 times Q raised to the power of 0.25. That's our average variable cost. Any questions on how I got that? Make sure you understand that step, because people often forget it, that they need to solve for labor in terms of quantity, and it usually winds up screwing up their calculations and their ability to solve for like variable cost expressions. What is your total cost? So we've got average fixed cost, we've got average variable cost. What can we do to get our average total cost? Add them together to get the average total cost, and then multiply by quantity to get to the total cost. So again, average total cost equals average fixed cost plus average variable cost. Multiplying the whole thing by Q, total cost equals average total cost times Q. So multiplying the whole thing by Q, the Q drops out of this term. We're left with just 1,225,000, our fixed cost, of course. And then, this multiplied by Q will get us to Q raised to the power of 1.25, because you're multiplying this by Q raised to the power of 1, so you add the exponents there. And another way to get this is just to get obviously the fixed cost and the variable cost equations that we solved for earlier, just throwing those together to get your total cost. All right, how are we going to get our marginal cost? Take the derivative of the total cost function, right? So the derivative of a constant is equal to 0. So we just take the derivative of our variable cost, right? So therefore, once again, highlighting the fact that marginal cost is the derivative of total cost, but it's also the derivative of variable cost, because that is the only cost that is changing. That's the only cost that's going to change as you're increasing the amount of output, the variable cost. Anyway, derivative, multiply the whole thing by 1.25, subtract 1 from there. So that's going to get us to, in this case, 11406.25 Q raised to the power of 0.25. Again, that's going to get us the marginal cost. That's going to be the equation of the limiting position of those secant lines that give you the slope of that tangent line at the point that you're interested in. And that slope is going to change as you're moving along the curve, because we saw that the curve is moving along. So you need an equation to represent the fact that the marginal cost is changing. So this is our marginal cost equation. How many films should you produce in a year to minimize your average total cost? So what was happening at the minimum of the average total cost? When we were looking at all the other curves, what happened at the minimum of the average total cost? It equaled marginal cost. That's the point where marginal cost crossed it. So how can we figure out how many films should be produced to minimize average total cost? Set average total cost equal to marginal cost. Exactly. So remember, here we were, marginal cost crosses average total cost at its minimum, starts to pull average total cost up. So that we're looking for Q3. What is that amount that will minimize average total cost? All right. So we're going to solve for Q here. So here's our total cost. We need our average total cost, which is this. We're going to set that equal to our marginal cost, which is equal to this expression here. So we have our marginal cost equal to our average total cost. And now we just need to solve for Q. So it's just some algebra here. So we subtract this term from this term. And that gets me this term here. Then we multiply both sides by Q. And that gets us to this. And then I divide both sides by 2281.25. And now we just need to raise both sides to what power? Or 1 over 1.25, yeah. So that means that the optimal amount of films that should be produced to minimize the average total cost is equal to 152.75 units. Any questions on this stuff? All right. Allocating production between two processes. In Chapter 8, we saw that the problem of allocating a fixed resource between two production activities, the boat example with the lakes, is solved by equating the marginal product of the resource in each. A similar problem, Gesundheit, a similar problem with cost is to divide a given production quota between two production processes in such a way as to produce the quota at the lowest possible cost. So will QT be the total amount to be produced? Q1 and Q2 will be two separate variables representing the outputs for the two separate production processes. Suppose the marginal cost in either process at very low levels of output is lower than the marginal cost at QT units of output in the other. So there's differing marginal costs. The value of Q1 and Q2 that solves this problem will then be the one that results in equating the marginal cost for the two processes. In the last chapter, we saw that the two production processes could have equal marginal products even though their average products differ substantially. The same happens with marginal costs. All right, so let's do this practice problem. Suppose production processes A and B give rise to the following marginal and average total cost curves. So marginal cost of production process A is 12 QA. Average total cost of production process A is given by this expression here. Marginal cost is given for the second production process is given by 4 QB. And here's our average total cost of producing in that second production process. So what is the least costly way to produce a total of 32 units of output is the question. So the minimum cost condition is that the marginal cost should be equivalent. And we're trying to produce 32 units of output. So therefore, the amount of QA plus the amount of QB should be equal to 32. So we're going to set our marginal cost of production process A equal to the marginal cost of production process B. And we have two different quantity variables that need to be solved for. Anytime you need to solve for two variables, you need two equations, or else you can't solve for those variables. If you have three equations, you have too many equations. Two equations, you need the same number of equations as the same number of variables you have to solve for that kind of system of equations. So here's one equation. Where's our other equation that relates QA and QB? So that just gives you average total cost as a function of each of those. What other relationship do we have that relates the two quantities to each other? QA plus QB equals 32. So that's our second equation there that we need. Here I just solve for QA in terms of QB. So 32 minus QB equals QA. So I plug that in for QA here. And now there's just an equation of QB. I can solve for QB. So distribute this out. 384 minus 12 QB equals 4 QB. Get all the QBs on the right-hand side. So we add 12 QB to both sides. That gives us 16 QB on the right. Divide both sides by 16. That means the optimal amount that should be produced in the B production process is 24. And now we've got one of them, so we can just plug that into either of our two equations to solve for QA. We know QA is equal to 32 minus QB, so 32 minus 24 equals 8. So that's how many units should be produced in the second, or in the A production process. 8 should be produced there, 24 should be produced there, and if that is the case, then that is the cost minimizing way of producing this output across both production processes, given that each one experiences a different average total cost curve, which represents like differing technology, differing wage rates. These might be different factories in different countries. They might be different factories in different regional areas where wages do differ even within countries. So the marginal cost of producing A is going to be 12 times A, which is $96, and the marginal cost of producing in B is going to be equal for 4 times 24, which is equal to $96. So that is why it is optimal, because each additional unit costs the same at that level of output. If it wasn't the case, if the marginal cost was less in one than the other, then you would want to obviously produce more at that production facility versus the other, because it's all about minimizing cost for the firm. So here we've got these, both of these marginal cost curves, and we see that at 8 units for this one, the marginal cost is 96. For this one, the marginal cost for 24 units is 96, and therefore in total, to produce the 96 at a 96 marginal cost, then 32 units can be produced, which is the most that can be produced given the cost limitations. So total cost, which can be derived by multiplying average total cost by the optimal quantities, winds up being, so total cost of producing A is going to be 400, total cost of producing B is going to be 1392. So we see that the total costs are significantly different across both production processes to produce, but what's most important is the marginal cost. That the marginal costs are equating, because we know that those are changing as we're increasing or decreasing the scale of production given the properties of the specific production processes. And so that is ultimately what always needs to be considered when we're considering how much decisions, how much of an activity to do. Well, I need to consider, what am I going to do next at the margin, that extra unit? How much is that going to cost me? I need to just think about the marginal cost. And therefore, if the marginal cost exceeds the marginal benefit, I do it. If not, it doesn't. Here, the marginal cost equals the marginal benefit, because again, by not producing it in one place, you're not producing it in another place, which is the opportunity cost of producing it at the one place. And if the opportunity cost of producing it at the one place is less, then you're going to want to do it at the other place until they're equal. Yeah. Yeah, right. Like they're plugged into the average total cost and then multiplied by the yeah, I actually did the math there, and then they're multiplied by the quantity, right? So there's our average total cost, and then there's our average total cost there, and then you multiply by the quantities, and then it gets you to the total cost. So this illustrates that the cost minimizing allocation does not require equality of total cost either, just that marginal cost be equivalent. All right, let's look very closely at the relation between marginal product, marginal cost, and average variable cost. In Chapter 8, we saw that the marginal product curve cuts the average product curve at the maximum value of the average product curve. In this chapter, we saw that the marginal cost curve cuts the average variable cost curve at the minimum value of the average variable cost curve. To see the connection, note first that from the definition of marginal cost, which again is a change in total cost with respect to the change in quantity, that is equivalent to the change in variable cost with respect to the change in quantity. When labor is the only variable factor, then this change in variable cost is equal to the change in the product of the wage times the labor. If wages are fixed, which they are, then the change in variable cost is equal to the wage times the change in labor. And so therefore the change in variable cost with respect to the change in quantity, which is equal to marginal cost, is equal to the wage times the change in labor with respect to the change in quantity. Using that fact, and you don't need to derive this, but this is all meant to just kind of highlight the connection between marginal cost and marginal product. So using the fact that marginal product of labor is equal to the change in output with respect to the change in labor, taking the reciprocal of that, we have the change in labor with respect to the change in quantity. So that's then therefore this expression is equal to 1 over the marginal product of labor, which implies that our marginal cost is equal to the wage rate times 1 over the marginal product of labor. So as the marginal product of labor is increasing due to increasing returns, marginal cost will be decreasing. This will be getting bigger. Dividing this by a bigger number gets us a smaller number. But then when we get into diminishing returns and marginal product starts to decrease, you're dividing this by a smaller number, which is increasing marginal cost. Also, average variable cost, we know, is equal to variable cost times quantity. Variable cost equals wage times labor divided by Q. We know that the average product of labor, the average amount that folks are able to produce at any given level of the productive input labor, is equal to the quantity divided by labor. Taking the reciprocal of that, L over Q means that average product is equal, average product can be expressed as 1 over the average product in this way, which means we can plug that in here. That means that our average variable cost is equal to the wage times 1 over the average product of labor. So our average variable cost is equal to that expression there. Our marginal cost is equal to that expression there, which demonstrates that marginal cost is inversely related to marginal product, and average variable cost is inversely related to average product. So again, here is our marginal product curve. Again, the slope of the total product curve. We have increasing returns, decreasing returns. Even past the point of our marginal product being at its maximum, where that change happens, where the short run wall is hit, average product is still being brought up because marginal product is still above it until they cross, at which point marginal product starts to pull down the average product of labor. At the point at which that happens, that's the same point at which marginal cost crosses average variable cost. Again, due to the fact that diminishing returns starts to pull up marginal cost at this point here, which corresponds to, so the minimum of marginal cost corresponds to the maximum of the marginal product. And once marginal cost starts to increase, average variable cost is still decreasing because, again, it is the inverse of average product. The average product is still increasing even when diminishing returns hit, which means that average variable costs are still decreasing until this point there where marginal cost is equivalent to it at the point where these marginal product equals average product, which is the point where marginal cost starts to bring up average variable costs. All of this is just really meant to solidify your understanding of the relationship between these concepts that are super important. The measures of productivity, how they relate to the costs that are going to be most relevant. And the patterns of that are really important because, again, those patterns are going to be the basis for comparing the benefits of operating in various industries to these costs. And so if you don't understand this, then you're not really going to understand why prices are set in the way they are in varying market contexts. So the minimum value of marginal cost corresponds to the maximum value of marginal product. The minimum value of average variable cost corresponds to the maximum value of average product. Quick exercise. For a production function at a given level of output in the short run, the marginal product of labor is greater than the average product of labor. How will marginal cost at that output level compare with the average variable cost? If the marginal product of labor is greater than the average product of labor, How will marginal cost compare to average variable cost? It'll be below it, right? And you can just see it from the graph, right? Over the range where marginal product is above average product, that's the range over which the marginal cost is below the average cost, average variable cost. All right, costs in the long run. Let's talk about the long run here. So choosing the optimal input combination. So again, in the short run, the firm is limited by the fact that they can't, change the amount of capital, which means the only way they can increase their output is by increasing their variable input labor. But in the long run, they can choose levels of all inputs. So the question is, what is the best combination of those inputs to choose in order to minimize costs? So no matter what the structure of industry may be, the objective of most producers is to produce any given level and quantity of output at the lowest possible cost. Equivalently, the producer wants to produce as much output as possible from any given expenditure on inputs. So they might have a certain budget that they're willing to spend on their capital and labor, and they want to get the most amount of output from that. So it's two ways of looking at the same problem. Either get the most out of like a certain budget or minimize the cost of producing a certain target level of output. Consider a firm that wants to maximize output from a given level of expenditure. Suppose it only uses L and K, labor and capital, with the rental rate being equal to $2 per unit of capital and the wage rate being equal to $4 per unit of labor. The question is, what different combination of inputs can the firm produce from a total expenditure of, say, $200 a day? So how we can represent that relationship is via what's called an iso-cost relation. It's a set of input bundles, each of which costs the same amount. So varying combinations of labor and capital, they cost the same amount. And it is analogous to the budget constraint. The budget constraint for a consumer was, again, the value of everything that they purchase that falls within their income. And we could, again, represent that as a line on an XY plane with good X on the X-axis and good Y on the Y-axis. Here we have input into production being labor on the X-axis and input into production capital on the Y-axis. So here is our ISO cost line. It represents the varying combinations of labor and capital that cost the same amount. So if the firm was to just use capital, they have a certain amount of cost they're willing to incur divided by the price of capital, which is R, and therefore this is the most amount of capital they could use to produce at this given budget that they have. Or they could just use labor, and therefore this is the most amount of labor they could use. Their amount of cost they're willing to incur, the budget divided by the wage rate. That's the most amount of labor they could use. So analogous to the budget constraint case, the slope of the ISO cost line is going to be the negative ratio of the input prices, just like the slope of the budget line was equal to the negative ratio of the price of the good on the x-axis to the price of the good on the y-axis. The slope of the ISO cost line is equal to the negative ratio of the price of the input on the x-axis, labor, which is the wage, to the price of the input on the y-axis, which is capital, which is the rental rate. So here is our ISO cost expression representing the fact that our costs are equivalent to the value of all the labor used and all the capital used. And we can solve for capital in terms of labor here. So I switched the sides here and then I subtracted WL from both sides. And now I'm going to divide both sides by R. And that's going to get me to the slope-intercept form for the ISO cost line. So the ISO cost line has, again, that y-intercept representing the most amount of capital that can be produced that can be used if only capital was employed, gesundheit. And then you've got the slope of the ISO cost line, which represents what, again, like the market rate of substitution between labor and capital. Each one has a market price, right, set in labor markets, set in capital markets, wage and R. And so this represents, again, the rate at which labor can be traded off for capital in open markets. It also represents like the opportunity cost of 1 unit of labor as we're moving from left to right on the x-axis. As you're using additional units of labor, you have to give up additional units of capital In this example, because our ISO cost line is a straight line that does not change, and again, that is the rate at which labor and capital can be exchanged in open markets because of their prices. So it is equal to the negative ratio of the wage rate to the rental rate. Finding the maximum output that can be produced for a given cost is similar to finding the optimal consumption bundle. So here are some ISO quants. ISO quants, again, introduced last class. They represent long-run production, the long-run production function in which both inputs into production are variable. Remember, it's a three-dimensional relationship. You slice it at one edge, at one level. That represents a level of output. And so the outer edge trace of that is an ISO quant curve. So this represents the varying combinations of capital and labor that can produce Q2 units of output. As we go out from the origin, each ISO quant represents a higher level of output. All right, so in this case, we're looking for the maximum output that can be produced for a given cost. So the firm has a budget, and they're looking to produce the most amount possible, so they're going to want to produce at the highest ISO quant possible. Obviously, this ISO quant is beyond their budget, so these combinations of inputs don't fall within the firm's budget. And these combination of inputs here, like this combination does fall within the firm's budget, but obviously the firm could produce more if they were on a higher ISO quant. So this is not optimal. None of these are optimal because the firm is not using all of its budget to produce output. So they want to use all their budget, so they're going to spend all of their budget, so they're going to produce on their ISO cost line. So therefore, this is the optimal input mix. The point at which the ISO cost, ISO same cost line, is tangent to the ISO quant, the highest ISO quant line, ISO same quantity, same quantity. So this represents the most amount of output the firm can produce given the budget that they're willing to spend. And it corresponds to this level of capital and this level of labor. So that's the optimal amount of each of those inputs the firm should use in order to maximize the budget and produce the most amount possible, which is Q1 units of output. The problem of producing the largest output for a given expenditure is solved essentially the same way. So let's say it's different. You don't have a budget, but you have a certain amount of output you want to produce, and you want to minimize the cost of that. So let's say the firm wants to produce Q1 units of output. The only difference here is that in the latter case, we begin with a specific ISO quant, then superimpose a map of ISO cost lines, each corresponding to a different cost level. So again, as far as like the mechanics of the ISO cost line, they work just like the budget lines. If the prices of the inputs aren't changing and we're just increasing or decreasing the budget, increasing the budget will shift the entire ISO cost line out. Decreasing the budget will shift the entire ISO cost line in. So this ISO cost line represents overall lower cost than this one, and this one represents lower cost than this one. So here is the amount of output the firm wants to produce. They can use any combination of outputs along it in order to produce Q1 units of output. This combination of output, which will use a lot of capital and a little bit of labor, will cost more than this amount of capital and labor. So they can produce this amount of units of output at the lowest cost possible, which corresponds to this ISO cost line. And therefore, once again, that point of tangency represents the optimal input mix selection, the cost minimizing mix of inputs to produce Q1 units of output. In the first case, the one in the last slide, cost was fixed and output varied. This time, output is fixed and cost vary. The problem is the same, though. They're trying to produce a certain amount at the lowest cost possible or get the most out of a certain cost that they're willing to incur. So recall from Chapter 8 that the slope of the ISO quant at any point is equal to the ratio of the marginal products of the two inputs, with the marginal product of the input on the x-axis being on the numerator and the marginal product of the input on the y-axis being on the denominator. It's also known as the marginal rate of technical substitution, as we mentioned. The marginal rate of technical substitution is diminishing from left to right. The reason for that is because earlier units of labor are assumed to be more suited to production processes than later units of labor. So, there's a certain amount of people that work to become really good at a certain trade, and so those people are going to be able to produce a lot. And so if you were going to trade those people out with capital, you would need a lot of capital to replace them in order to maintain your level of output. So the marginal rate of technical substitution is pretty big along this early range of labor. But as you hire more and more people, you're likely to hire more and more people eventually that aren't necessarily specifically trained for your production process. And so they're not going to be as efficient as earlier units of labor. And so the marginal rate of technical substitution will be lower for those later units of labor. And that's why the slope of the isoquant gets flatter as we move from left to right, which means that we have diminishing marginal rate of technical substitution, which reflects the fact that the inputs into production are not perfect substitutes. They're imperfectly substitutable. They can only be exchanged at different rates, again, depending on how well suited the productive input is for a production process. And earlier units are usually going to be more suited than later units, which again is in contrast to the cases we looked at last time, where you had the linear isoquants representing the perfect substitute case, where we looked at inputs of different gasolines that can be used to produce trips. And those isoquants had just straight lines, marginal rates of technical substitutions that were constant, versus the fixed proportion production function, the Leontief production function case, which represents another extreme end of the productive spectrum where the inputs are complements to each other. The only way to increase output is by increasing both inputs in a fixed proportion, which led to like right angle isoquants, in which there was no marginal rate of technical substitution because you can't substitute them for each other. This is the most common case. The inputs are imperfectly substitutable for each other. We capture that by a diminishing marginal rate of technical substitution, which means that we have these concave isoquants. So the marginal rate of technical substitution is equal to the ratio of the marginal product of labor to the marginal product of capital. So it follows that at the optimal input mix, where the firm is either maximizing their output for a certain budget or minimizing the cost of producing a certain amount of output, that at that point, the slope of the iso cost, the relative price of the two inputs, is equal to the slope of the isoquant, which is the marginal rate of technical substitution. And so at that optimal point, the marginal product of labor to the marginal product of capital is equal to the wage over the rental rate. We can again rearrange this expression to get a more intuitive idea about what that equilibrium means. So cross-multiplying them gets us to this expression here that tells us that at the optimal point of cost minimizing for this output quantity, the marginal product per dollar spent across all inputs is going to be equivalent. So a dollar spent on labor or a dollar spent on capital at this point will yield the same amount of additional output. Whereas if we are like at this point over here, the marginal rate of technical substitution is greater than the relative price, and so therefore the rate at which the firm can switch out the inputs for each other values labor a lot more than the rate at which the firm needs to switch them out in terms of the open market prices. And so it makes sense. And what it also means is that the marginal product per dollar spent on labor, the extra amount of output per dollar spent on labor over here is going to be greater than on capital. So the firm should use then less capital and more labor because they can get more output per dollar spent on labor. And then and so they do, and so they move down their ISO cost line to that point. But due to diminishing returns, eventually the two become equivalent. And the same is over here. Over here, the marginal product per dollar spent on labor is greater than the marginal product per dollar spent on capital, and therefore each additional dollar spent on capital will yield more additional output. And so it makes sense for the firm to use less labor and use more capital and move to that optimal point. The mechanics of it work exactly the same as the optimal point on the rational consumer choice model, where the marginal utility per dollar spent was equivalent across all goods at the optimal consumption bundle. And so the intuition, the mechanics, the mathematics are all the same. If you were able to learn that stuff to a decent extent, then it should help you to kind of like to grasp what you need to understand about these relationships. So this implies that for cost to be at a minimum, the extra output we get from the last dollar spent on an input must be the same for all inputs. The result is robust to the n input case, meaning that if we go to the more complicated realistic cases where there are more than two inputs, again, the cost minimizing mix of all inputs will occur at the point where the additional product per dollar spent across all inputs, regardless of how many there are, is equivalent. All right, folks, we're done for the day, so you can relax. I'll see you guys on Tuesday. Have a good weekend. I already opened up the mini paper for the last chapter, chapter 8, and the homework. And then anything else that pops up beyond that next week, we'll be doing at the end of spring break. So that'll give you a little bit more time to work on some of that stuff. All right, have a good weekend, everyone.